Hi, my name is Dave Davis. I'm an acoustics engineer from Australia. I presented this paper at the IN21 Conference last month. This year the conference was held in Washington, DC. It's the biannual conference of the International Institute of Noise Control Engineering. The paper describes a method that I've developed using the Monte-Carlo simulation method to predict the variability of noise emissions from construction sites. Usually, when construction noise is modelled, it's typically modelled fairly simplistically. Usually, the sound emissions from the noise source or noise sources are assumed to be a constant. And usually, the propagation of the sound from the noise source or sources to the receiver or the receivers is also assumed to give a constant attenuation of the sound. And that means that the predicted sound levels at the receiver or receivers is also assumed to be a constant. Now that's a very simplistic approach, and it isn't very realistic, because the noise emissions from construction sites are quite variable usually. So in practice, in reality, the sound emissions from the noise sources are variable, and you could in fact quantify them statistically. And the attenuation between the sources and the receivers is also variable. So you could in fact quantify that statistically if you wanted. The variability of the sound received at the receivers is going to be due to the combination of the variability of the noise emissions from the sources and the variability of the propagation attenuation. So the variability at the receiver is going to be worse than either of those two factors combined. Now, if you had one noise source which had different sound emissions at different times so that its noise emissions were variable, you could probably build a sophisticated model and try to predict all the different received noise levels at the receivers due to the variability of the noise emissions from that one source. But what if you had a construction site with lots of sources? Well, that wouldn't be quite so easy. So the fact is that the noise emissions from many machines and activities on construction sites are highly variable. And for construction sites, the phenomenon of the variability is that it usually occurs primarily in time space. So that means that there usually isn't very much variability in the frequency spectra of noise emissions from individual noise sources. The causes of the variability from each noise source is usually just because the different tools and machines are they're being used or they're not being used. They're either on or off. They're either operating or they're idling. So the variability of each noise source is really just a case of it's on or off most of the time. Other kinds of variability from different noise sources could be that some machines are moving. So, for instance, like a truck, they might move different places around the site. So the noise emissions from those noise sources are changing. And also the propagation of sound from those noise sources to the receivers would also be changing just because of the changing distances between them, and also because there'd be a change in the acoustic attenuation due to other things like shielding from terrain or structures. Now, another kind of variability on construction sites is that some machines actually perform different tasks. So, for instance, you might see an excavator. At one point, it's digging, and it'll go to a different part of the site, and then it will change its working implement from a digger to a hydraulic ram, and it will start, for instance, breaking rocks or breaking concrete. Now, the Monte-Carlo method gets its name from the casino at Monte-Carlo. It's based on the principles of chance, which is, of course, what happens at casinos. So, the way you convert the idea of chance into a mathematical modeling simulation method is you use statistical calculations. So the way we implement the method using a computer is like this. First, we predict the component contribution noise levels from each individual source at each receiver. We then use a function that we have written to combine the noise from each separate noise source at each receiver, but you allow each separate noise source to be either on or off. You then use a flag switch in your calculation to designate whether that noise source is either on or off. And then you iterate over a loop, changing that flag switch. You use a random number generator to decide whether each individual noise source is operating or not, based purely on the percentage utilization of that noise source. How much time, what percentage of time is that noise source on compared to the total amount of time? And then you just calculate the sum total noise level at each receiver from the combination of all of the on noise sources. And you store the predicted noise levels from all of the combined on noise sources at each receiver for that loop iteration. And then you repeat the loop over and over again. You repeat that calculation many, many times, and that's the Monte-Carlo method. You simulate the idea of chance and statistics by letting the situation exist in many different instances, many different cases. So this is a representation of what the calculation looks like in your computer function. Each time you calculate an iteration, you calculate the noise level at each receiver from each source, only if that noise source is on. And the noise source is only on if that random number generator compared to the percentage utilization of that piece of equipment on the construction site says that, according to statistics, for this iteration, that noise source is on. So let's have a look at an example. This is an imaginary construction site, a fictitious construction site, which has a number of noise sources. And for each noise source, we have a sound power level. So we know how much sound that noise source emits while it is on. And we also have an estimate of the percentage of time that that noise source is on, that it is making noise. So we have the percentage utilization of that piece of construction plant on that construction site. And this is the bare minimum information that you need in order to do this calculation method. So now if you plot the total sound power level of all of the combined noise sources that are on at any moment in time, you get a chart that looks a little bit like a timeline. So this is not a timeline, but you could consider it to be one. And you can now start to appreciate the power of this method, because you can imagine peaks and troughs in the sound emissions from a site where some of the noise sources are turning on and some of them are turning off at any moment in time. So you can pretend that it is actually a timeline. And if you did 1,000 iterations and you considered each iteration to be a minute, then you would get a typical day's worth of noise emissions. So what we've just done is we've actually estimated the statistics of the noise emissions from the site. We've come up with a way of estimating the variability in the noise emissions from the site. Now, I'm not going to do the variability in the propagation attenuation from the sources to the receivers, because that is already very well understood. Just for an example, you just imagine you can consider a windrose that has the statistics built into it. So I won't go into that here. But if you do incorporate the variability of propagation attenuation and the variability of the noise emissions, then together you will get an estimate of the variability in the sound levels received at the receivers. So if we have the propagation attenuation from the sources to the receivers, and we apply that to our noise emissions in all of our 1,000 samples, then we can now estimate the variability in the noise levels received at the receivers. And we can estimate statistical parameters such as the Lmax, such as the minimum, the Lmin. We can estimate the overall average and all of the other statistics. So we can now put that through standard statistical calculation algorithms. Now, the thing about the Monte-Carlo method is that every time the simulation is run, you get a different answer. So this is multiple calculation runs, and each run has 1,000 loop iterations. And you see that the time trace is clearly very different each time. The statistics of each noise source turning on and off changes each time. But the main statistical information, which is the percentiles of the maximum and the minimum, they don't change very much. Each time the simulation is run, the results are slightly different, but not very different. And typically, these are the kinds of answers you would want. You'd want the minimum, the maximum, the statistical average, which would be the 50th percentile, or the energy average. You would want the 90th percentile, for instance, the 10, and you can see the range is quite large for our fictitious imaginary construction site. But you can imagine that if we had have assumed that all of our noise sources were constant, if they were all on when we did our noise modeling, then that is the noise level that we would be reporting. That is the noise level that we would say is going to be received at the noise receiver. Or the other way around is if we had each noise source adjusted for its percentage utilization in terms of energy, then this would be the result that we would say is being predicted at the receiver. So in fact, both of those values are wrong. Neither of them is the truth. The truth is you have a statistical range to deal with, and that is the valuable information. So again, every time the simulation is run, the results are slightly different, but the statistics generally don't change very much at all. The statistics are very stable. So it is in fact quite a reliable method. Now I've found that you need approximately 1,000 iterations of your loop in order to get stable statistics for the kinds of construction noise sources that I've looked at and the percentage utilizations that I've come across. About 1,000 loops of the iteration gives good stable statistics. And if you analyze your data that you get after doing your loop iterations, then you might be tempted to think that these probability distributions are believable if you use fairly wide data bins. But in fact, if you use fairly wide data bins, like approximately at 1 decibel, then the cumulative distribution doesn't match the percentiles very closely. So I have found that if you use a much narrower data bin width for your probability density, then the probability density graph isn't very neat, but the cumulative distribution graph is very nice. The cumulative distribution matches the percentiles very well indeed. And again, every time you run, you get a different result. So you see that the probability density graph changes quite a lot each time you run it, but the cumulative graph doesn't. And what you do find is that if you have wide data bins, then your cumulative distribution doesn't match your percentiles. But if you have very narrow data bins, then your cumulative distribution does match your percentiles very closely. This is purely a function of the number of iterations. If you ran your loops many thousands of times, then the probability density graphs, whether the data bins were wide or narrow, would be very similar. And the distribution, the cumulative distribution, would match the percentiles, even if you have quite wide data bins. But we only have 1,000 loop iterations, and I've found that that's good enough to give you good information, but I do recommend that you use quite narrow data bins.